Okay, so we're going to take the disk method and shell method, and we're going to analyze them and look at their differences. And so first we're going to start with the disk method. So the disk method is going to be in a situation when you have a graph, and you want to rotate this graph. You want to find the volume. Let's say we want to rotate it on the x-axis. Okay, so first you have to know the area of the cylinder. Essentially, what you're making a cylinder. And you're making an infinite amount of cylinders under this as you rotate this graph. Okay, so you're gonna imagine it being rotated like so. So you have a 3D object that kind of looks like this. And so you're going to take this little representative rectangle, rotating it around the x-axis, always perpendicular, and what you're going to do is you're going to find the volume of it. And so you know the volume is going to be pi r squared, and then you're looking for the change in volume, so it's going to be change in x. Okay? And so what this is basically the volume of a cylinder. And so first you have to know, the first thing you need to figure out is what is r squared. R squared is going to be the radius, so it's going to be essentially the distance from your axis of rotation to the point on the graph where you're making the height, essentially, of your little representative rectangle. So in this case, let's say this is something like y equals x cubed. So r of x is what we'll call it. We'll call it r of x equals x cubed. And what you're going to be doing is you're going to be squaring this value, because at any value x, it's going to produce your height. You're going to be squaring this, so you're going to say the volume equals pi. You're going to take pi out, your integral from a to b. And so when you rotate around the x-axis, your a and b values are always on your x-axis. So maybe from here to here, from a to b of x cubed squared, and then your dx, and you'll integrate this. And it'll make an infinite amount of little bitty cylinders, and it'll add up the volume. That's what you'll get here. Now, also, this would work if you wanted to rotate it about the y-axis here. If you wanted to rotate it about the y-axis, now your area, instead of being what's under the graph, is going to be right here. This is going to be your area. And so what you're going to have to do, the difference is when you rotate it here, everything's going to have to be in the function evaluated with respect to y. So if this was y equals x cubed, now it's going to be the cube root of y equals x. And so what you're going to do is now the height, or the r of x value, is going to be the cube root of y minus, so the right-handed function, I guess you could call it, minus 0, or whatever the function is on the left, minus 0. And one thing I forgot to mention is it's top minus bottom. So when you integrate around the x-axis, you're taking your top function, whatever that may be, subtracting it from your bottom function, which it happened to be 0, so we just implied it was 0. But now back to the integration with around the y-axis, the volume, let me change pens real quick, the volume is going to equal pi times the integral. And now that you're rotating around the y-axis, you got to take your integral, the limits of integration now become y points. So if you want to integrate maybe from 0 to some value of here over y, and right minus left, like we said, so this would be the cube root of y minus 0, and you want to square it and take it with respect to y. Everything's with respect to y. So that would be a quick overview of the disk method. Now we're going to talk about the shell method, which is a little bit more complex and hard to visualize. But it works in different situations actually better than the disk method does. So the shell method is what you're going to essentially do is you're going to make little shells, and you're going to integrate a bunch of little shells together. You're going to add up the volume. So you'd have something like this, some shell, and the volume of this shell is actually going to be the volume with respect to the outer radius minus the volume with respect to the inner radius. Okay, so this would be pi r of x would be this big value right here, and then r of x squared, and then minus pi times the little r of x, which is going to be this inner value. And when you simplify this, actually what it comes down to is the volume equals what we'll call p of x. This is the average value from your axis of rotation to the center of a representative rectangle, which I'll get to in a second. P of x times h of x, which is the height, and then dx. And so what this is, and so you can visualize it better, we'll make a graph. So let's say we wanted to integrate something like this, and we wanted to rotate it about, we'll say, the y-axis. So what we'll do here is we'll make representative rectangles, and instead of them being perpendicular like they were with the disc method, perpendicular little discs, we'll make shells that are parallel. And if you can imagine what this will do when this shell rotates about the y-axis, or when this rectangle rotates, it's going to make a shell. And so what we already established, the volume, or the change in volume I should add, is the distance, the average distance from the axis of rotation here. So it's usually going to be x, except for other scenarios when you're not right up against your axis of revolution. Like for instance, if you were maybe, let's say, rotating around here, we'll say this is x equals 5. You're rotating around here, your actual value of x, or your average radius, your p of x value, would be 5 minus x. But for this one, it's just x. So we can forget this. So anyway, so your p of x, and now you have your p of x value here. So we established p of x equals x. But now you need your h of x, which is your height. So what you have with the height is basically top minus bottom. What is top minus bottom? And so your h of x is going to be the top of your representative rectangle, which in this case corresponds to this graph here, whatever it may be. So we'll maybe say it's like a x squared plus 1 minus the bottom, which is 0. And so, and what you'll end up getting, you're going to end up getting the volume equals 2 pi. We integrate 2 pi now. It's because when it simplifies, the complex formula is something like pi times, and it's like w minus p over 2, stuff like that. You don't need to know, but anyway, what you end up getting when it simplifies is 2 pi times the integral, and then you'll be integrating. You're rotating around the y-axis. It's everything is kind of like flipped from the disc method. So now pi becomes 2 pi, and now instead of integrating from 0 to the top of the y-axis, you're now integrating from 0 to here, because think about it, these rectangles are going this way. So you're taking a rectangle there, you're taking one here, you're taking one here, you're taking one here, and because you're going this way, you need to integrate on the limits of integration are x values. So you maybe from 0 to some x value here, whatever that may be, like 4. And so you have your integration. Now you just set it up with p of x, x, and then times h of x, which is x squared plus 1 with respect to x. And you integrate this, and you'll get the volume. And it's worth noting that if you were to integrate with the disc method, you would need 2 integrals, because with the disc method, this is where the shell method is kind of better than this method in certain situations. You would have to integrate from here to here using your perpendicular rectangles, and then from here to here, because your right function, your left function changed. From here to here, your right function is right here, and your left function is right here. But from this point on, your right function is still this, but now your left function, it becomes this graph right here. Okay, so now let's do a problem. We'll do a problem real quick. And let's see here. So we'll do a problem. So we'll have a graph. We'll have a graph. And we'll be using y equals x and y equals x squared. And we want to find, so we have y equals x, right, coming right through here. And we have y equals x squared coming here. And we want to find the volume of the, I guess, the volume of these intersection, but the volume between these graphs when you rotate around the x-axis. And we'll use disk method first. So with this method, you're rotating around the x-axis, okay, so you can get your representative rectangles and they're perpendicular. But what you have is when you rotate this, you're going to have actually a hole that's going to develop in this region right here. When this region rotates, there's going to be a hole. So you need to find a way to find this. You're going to have to actually subtract that hole off. And the way we do this is we're going to make, I guess we're going to rotate it, we're going to find the volume as if this were as if this hole weren't there, and then we're going to find the volume of this hole. So we have essentially two different functions, and we'll call the big function, or the greater volume, is going to be produced when you integrate under the y equals x curve. We're going to call that r of x, and we're going to set that equal to x. And then we're going to integrate underneath the x squared. This is going to be the smaller volume, the volume we need to subtract off. We're going to call that little r of x. And what this is going to be, it is just going to be x squared, because this is the top function, x squared minus the bottom function. And this is also x minus 0, because we are, if you can see what we're doing here, we're taking the top function minus the bottom function, and then we also have this top function minus this bottom function, and this is the area we're subtracting off. And so when we get the volume, what we're going to have is the volume equals the integral pi times the integral. And so I'll slow this down for you. We're going to first take the big function. So it's going to be pi r squared, and the radius is going to be r of x. So pi times x squared dx, and we're integrating from 0 to 1. This is, oh yeah, and we also always need to find the intersection point between these two graphs, the x and y value. And in this case, we only need the x value. And so we can do that by saying x squared equals x squared minus x equals 0. And so they're going to intersect when you take this. X equals 0 comma 1 is the intersections. And we have 0 here, and we have 1 up there. So we have the integral from 0 to 1 of x squared plus pi times the integral from 0 to 1 of the little r squared. And so we have x squared squared dx. And people shorthand this a lot. They actually simplify. They say we can pull out a pi, and we can actually, in a way, pull out this integration 0 to 1 of x squared. Oh, my bad. I made a mathematical mistake. I said plus. This is actually a minus here, because we're subtracting off this little area from this big area to get the area in the middle. And so it's going to be minus x squared squared with x to the 4th dx. So a lot of times you'll just see it shorthanded like this. And so when you take the volume, you're going to keep out pi from 0 to 1 of x squared dx minus the integral from 0 to 1 of x to the 4th dx. And so then you're going to have volume equals pi times 1/3 x cubed, and you're going to keep this outside. X cubed evaluated at 0 and 1 minus 1/5 x to the 5th evaluated at 0 and 1. And then when you simplify, you're going to end up getting 2 pi over 15. That's going to be the volume. And so that's how you use the disk method. Now, we'll do it one more time with the shell method to show the difference, and if we do it right, we'll get 2 pi over 15. So we'll come over to this corner here. So we have our x squared, and then we have our x here. So this is, we already established it as 1 comma 1 is the intersection. This is 0, that's the origin. So we're still integrating around the x axis. But now, since our representative rectangles are parallel to our axis of integration, or our axis of revolution, not integration, everything becomes, we integrate in dy, so we need to take everything with respect to y. So what we have here, we had y equals x squared. Now we're going to use x equals the square root of y, plus or minus, but we only need the positive. The minus sign is irrelevant at this point, because it's in the positive quadrant, the y positive quadrant. And then we also had y equals x. So we can just flip that and say x equals y. So, first things first, we need to find our p of x, or the average radius. And that's going to be from the 0 origin up into some point in between here, and it's always going to be y. So we say p of x equals y. Now we also need to find h of x. Now h of x is the height, and the height of the rectangle is the function evaluated on the right minus the left. And so our right-handed function now is the square root of y, and our left-handed function is y. So this is the height at all situations within this integration. So now we take the volume equals 2 pi, the integral, and so now we're integrating with respect to y. So we start at 0 and we go all the way up here to 1 of the average radius, which is y, p of x, times h of x, which is root x minus y. And we're taking all this with respect to dy. So now we can just simplify it out. We say volume equals 2 pi times the integral from 0 to 1. We'll multiply y times y to the 1/2. We get y to the 3/2, minus we multiply y by y, we get y squared dy. So now it equals 2 pi times, we put this integral, we integrate both y to the 3/2 and y squared. We need dy here and dy here. And so then we can take 2 pi and we can take y to the 5/2 divided by 5/2, evaluated at 0 and 1, minus y to the 1/3, y cubed to the 1/3, evaluated at 0 and 1. And then when you take this function, when you take now this solution, you're going to end up getting 2 pi over 15. And that is the shell method. The same problem uses the shell method to solve. You get the same answer. Thanks for watching.